Dr. Darren, I think we can start. I will just start with the, as usual, our symbolic lamp lighting. By that time, it will be sharp 6.
Okay.
With your permission. Namaskar and very good evening to all of you from India, and good morning, good afternoon to all of you wherever you are, and welcome to the technical keynote session 6 of virtual conference on disaster risk reduction, civil engineering for a disaster resilient society. So welcome to all the speakers, welcome to all the participants, and welcome to our chair of this session, Dr. Darren Xian from National University of Singapore. So let me briefly introduce the session chair. Professor Darren Xian is an associate professor and associate head of research at National University of Singapore. And he obtained his PhD from Cambridge University, and his contribution in the field of earthquake engineering, catastrophe modeling, landslide, and in vulnerability assessment of underground structures are very popular. He received a grant from the UK Engineering and Physical Science Research Council as a geotechnical specialist to carry out several post-reconnaissance missions in several earthquake events. Professor Xian was named as a top innovators under 35 in Asia by the MIT Technology Review for his innovative contribution in catastrophe modeling in the year 2016. He is also an IRDR Young Scientist under the United Nations Office for Disaster Risk Reduction. He also served as several positions, especially as Vice President of Singapore Geotechnical Society, and several committee membership he holds, especially in the ISMG and other internationally recognized societies. So we are honored to have Professor Xian with us to chair this session. Now I hand over the session to Professor Darren, please.
Hello, hi. Hello, hi. Good evening. It's a great privilege for me to be, to be chairing this session where we have 4 eminent speakers who will be sharing the state of arts of their respective areas of research interest, and let's move on to the first speaker. Okay, our first speaker is Professor Dr. Jasmine Siu Lee Lam from Nanyang Technological University in Singapore. She is an active scholar in maritime transport and supply chain research. She leads a research team and has been working closely with the industry and government agencies. Prof. Lam has completed over 50 R&D projects and published more than 270 publications in leading international journals, books, and conferences. She holds several prestigious international appointments and is also the recipient of many awards, including the National Day Honours Commendation Medal awarded by the President of Singapore, 8 times Best Paper Awards, Eagle Prize, and Erasmus Mundus Scholars Award. Without further ado, let's hand over to Prof. Jasmine Lam to begin her keynote speech. Prof. Lam, please. You can share your screen. Yeah.
Yes. Hi. Hi. Hi, everyone. It's my pleasure to be here in this conference. I am very glad to see that there are so many participants, even it is a virtual conference. So we see each other online. Of course, in the near future, of course, I do really hope that we can see each other face to face. Now let me share my screen. Just a moment, please. I think you can see it, right?
Yes.
Yes.
Okay. All right. Yes. Okay, so let's begin. As mentioned by our session chair, I'm from Nanyang Technological University in Singapore. For today's topic, it is on integrated cost and risk management enhancing supply chain resilience. So that's why there are a few keywords, as you can see from the topic: cost, risk, and supply chain resilience. Especially for today, nowadays, there are so many risks and disruptions. And my focus is on supply chains, and I'll explain a little bit very soon as well. The supply chains are exposed to various disruptions. I think nowadays, because of the pandemic, COVID-19, that's why we are all in a virtual conference. This is one of the key major disruptions that we are encountering. Who knows? I mean, maybe in the future, some other kinds of disease or whatever. So that's why we have to be prepared. Labor strike, natural disaster, computer virus, or there are many other examples as well. Then under which I think in this conference, we also focus on disaster. There are so many different types of disasters. It could be earthquake, it could be typhoon or hurricane. It could be many other natural disasters related to climate, related to weather. So all these are somehow unexpected and uncertain, and I would say undesirable. But just that these are unavoidable. That's why the key point is that how to mitigate or how to become more resilient. And why resilience really matters? We talk about resilience. One of the key reasons is that because of globalization. Globalization has been with us for the past, for example, 20 years or so, largely because of more open trade and also more open economies, and different companies and countries, they trade with each other. There are, of course, a lot of benefits, a lot of advantages. And we do see many countries, many companies prosper and benefit from globalization. Just that it's not just about the benefit or about the pro. There are also cons of globalization. And we do realize it, especially actually now during the pandemic, because of the interaction, because so many different trades and different people's interaction in different parts of the world. When there is a disruption, it could be spread more easily to other countries, to other societies. So that's why when we have to evaluate risk and resilience, it is important to, of course, evaluate a particular entity or a corporation. And not only based on just the individual corporation, but largely speaking on the supply chain performance on the supply chain. And also to note that competition nowadays is largely based on supply chain. That means we compare one supply chain versus the other supply chain, not just one company versus another company. Because of all these reasons, that's why my focus is more on supply chain resilience. And another related reason for the importance of supply chain resilience is also because of the domino effect. when a node in the supply chain breaks down, or when there are disruptions or anything goes wrong, then the whole flow, the whole supply chain may be disrupted. Okay, so this is the effect, and that's why the effect or the impact can be huge, and it affects not only one entity, but it could be the whole system. Therefore, we need resilience to bounce back quickly after any disruption that I have mentioned, be it natural disaster, pandemic, or any other kinds of disruptions. Here, I would like to go through briefly about risk and risk classification, because this is also a keyword in the topic, under which I focus more on supply chain risk, okay? Because when we talk about risk, I think because of the theme of this particular conference, many of us work on risk and related topics. We know that there are so many different literature, research on risk as a whole. So that's why we need to zoom in, okay? But even under supply chain risk, there are so many different things. And you can see here, I broadly classify into disaster, disruption, delays, and deviations. And then, because my expertise is more on transportation and logistics and also supply chain, so that's why here I zoom in more to transportation disruption. There could be other disruptions as well. For example, there could be production and manufacturing disruptions, many other types of disruptions in the supply chain as well. But just that I choose to focus on transportation disruption, that the research can be more manageable, and we need to be focused. And then also under transportation disruption, there could be two kinds of flows: material flow and information flow. Material flow refers to more related to physical flows. That means those related to cargoes, goods, and something more tangible. And then information, of course, we know that nowadays information is the key to many things. So that's why information flow affects also the material flow. So the two are, of course, very closely related. And for both material flow and information flow, we have internal risks and external risks. Internal risks, when I classify internal, those will be more internal to a particular corporation or entity. That means the focus of the subject matter, it could be a particular company, it could be an organization, or it could be a particular city. So it depends on the subject matter. External will be something less controllable, which will be outside the control or outside the management of the particular entity. So that's why we have both internal risks and external risks. Then here in this particular talk, I would like to share on the analysis of existing strategies on how to improve resilience. So that means we know that there are different kinds of risks. The key is that the key question is how to improve resilience. And I have summarized some key strategies, including a few ones like cooperation and alliance. So since I have mentioned that I focus more on transportation, so that's why there are some examples related to transportation or this particular industry or sector. Let's say transportation companies, the carriers, they could be trucking companies, they could be freight forwarders, or logistics companies, shipping companies. So that means they are the ones to carry the cargoes, to handle the physical flow of the goods. They form alliances. And in this case, let's say shipping companies, they form alliances, and these are, of course, legal alliances. Individually, they are in an individual company, but at certain places, let's say in terms of routing, in terms of sharing certain assets, they are able to cooperate in order to compete. So that's why they form alliances. And I would like to explain some more later on as well. I will show a particular table, but here I'm more on a higher level view. So another type of strategy to enhance resilience is also to invest in redundant capacity. So that means in a generic term or layman term, just to have some buffer. All right, we cannot be always very, very tight in terms of any capacity. And in view of the focus of transportation, so let's say your vehicle, your fleet, in terms of the number, in terms of the size, in terms of the people who will have to drive these vehicles, let's say all these resources need to have certain redundant capacity or some buffer capacity. Next, adding control. Adding control means that you need a particular, for example, a system to monitor and control the situation and to know what is going on, for example, in terms of the movement of the goods, in terms of any particular incidents, in terms of disruptions or foreseeable risk. So in that case, it could be your particular distribution center to see any particular, you can have sensors. You can, for example, making good use of technology in order to enhance the ability to monitor and to control. Responsive pricing is another type of measure. With responsive pricing, why is it important? So I see from the angle from the commercial point of view, that means actually pricing is to regulate the demand side and the supply side. This in a way also relates to the capacity and the market's demand, and then also how responsive you are as an entity or as a company. So in that case, your pricing should also be responsive to the changes and disruptions that you foresee or you are encountering. So this is also one of the strategies that companies are already using. And then now here, because we mentioned also that information now is very, very important. And also we all hear a lot of buzzwords now, like digitalization. We know digitalization is very important and now is very prominent. And in view of, for example, the pandemic, this is even more highlighted by many countries, by many companies to accelerate the pathway to grow digitalization, to become more digital. And let's say, for example, having backup of your information system, of your data warehouse, all these will help to have resilient information system. So this is another type of strategy that companies have to use for enhancing supply chain resilience. So here I just would like to share a table. Just a moment. So I guess you can see this new screen, okay? So because it's a very big table, so that's why I think it's easier to show here. I can't fit all the content into 1 or 2 slides. So here, this is what I mean. In the particular research, these are the strategies that I've mentioned just now. Then I have provided examples, real life examples in practice, and we can take reference from this. And then also the particular objectives and advantages For example, just take an example of cooperation and alliance. The major objective is to have quick recovery after transportation disruption, meaning that, for example, if your own fleet in one company fails to perform, there will be quick replacements that can be obtained from your partners. So in this case, also that you do not have to invest or have to, for example, purchase all the equipment that you need, and you can rely on your alliance. Of course, then this kind of alliance will need trust, and there are also a lot of coordination, definitely. That's why in view of that, since there are some advantages, but it's not just a perfect, we need to analyze the difficulties and the disadvantages as well, meaning that we know the pro and con, and then also the examples of related risk events, meaning that in reality, what types of risks, because remember, I've shown you the classification of risk. So let's say internal risk, external risk, under which then what kind of risk can be tackled by this type of strategy, and the relative references as well. So likewise, investing in redundant capacity, responsive pricing strategy, adding control, and then also resilient information strategy. So this is how I analyze the different types of strategies, and hopefully this will help, for example, different companies and even like other researchers who would like to embark on this particular type of research to understand the different strategies. And of course, there could be new strategies coming up as well. So I think this particular framework can also help different researchers and analysts to structure the different supply chain resilience strategies. And back to just now the slide. Yes. So after what I have considered in terms of the pros and cons, objectives, real-life examples of these strategies, one important thing is that something is missing. Because in the literature and also in terms of, for example, market reports or industry information that I can find from my research, largely speaking, those sources do not really touch on much or very little about cost. Okay, meaning that we understand that it is important to incorporate these supply chain resilience strategies into any company. However, cost is also another concern, because we do know that in reality, if you incorporate more strategies, there could be higher cost. So that's why the question here is how to maintain the balance between cost and being more resilient. That means a company has limited resources, and you just can't continue investing in different kinds of strategies. For example, just take one example. Let's say to enhance the information system to become more resilient, to invest in digitalization. We know that these are very beneficial. Just that cost is the real concern as well, right? And also noting that risk or this kind of disruption does not happen every day. That's why companies, from the commercial point of view, they always have to understand and always have to analyze how expensive or what is the break-even point, and how do they incorporate all these considerations. So that's why here in this research, this is a new element in this particular domain of research, is to have both resilience and also cost-effective solutions. So that's why I have added the bargaining power analysis in terms of these particular strategies like cooperation and alliance, adding control, responsive pricing. Why? Because these involve alliances, partnerships. So that's why, and also like, for example, the supplier and buyer relationship. So that's why here, what's the bargaining power of your firm versus the other particular entity. So this is about bargaining power analysis. Then also cost analysis. Here, for example, it relates to investing in redundant capacity and resilient information system. So I think I have explained this part. So that's why together, the main purpose or what we want to really achieve is to combine the bargaining power analysis, cost analysis, and to achieve an optimum resilient solution. Meaning that given the different choices of resilient strategies, which ones would be more appropriate and what is the cost, all these will really help companies and corporations and organizations to adopt the most appropriate strategies. So here there are some suggestions on how to achieve this in terms of an integrated risk and cost management resilience model. So let's say we can make use of decision tree. So this is one of the techniques that we can deploy to, for example, to analyze a type of strategy to improve resilience. So that means a particular company can choose one, or there are several ones to analyze. And then here, as mentioned, because we would like to analyze or incorporate bargaining power, and that's why we have high, medium, and low bargaining power. So there are different scenarios. And then the next layer is the responsive pricing, adding control, forming alliance, etc. So these are the strategies that I have introduced. And then also there are different under which, because of the technique of decision tree, so there are different scenarios that we will analyze as well, like optimistic, most likely, pessimistic, and then what is the cost involved. So that's why at different layers, there will be different permutations. And this helps ultimately to understand what is the probability, for example, and then also how companies can make better decisions. So just quickly, in view of time, so I think here we can make use of some real examples from various sectors. So let's say transportation companies, just like here as a container shipping line. So this is one of the examples, like analyzing the market share and the bargaining power, and then we can incorporate decision trees. So I think I will skip this one. This is just to analyze how high the bargaining power is based on market share. So I will leave the details. So that means as a whole, budget and cost would be the key components in this particular system. So meaning that even we talk about resilience, how to enhance these and how to incorporate the different strategies, a very important thing is also to think about a more cost-effective solution. So this is the overall point. So that means, in summary, there are certain new ingredients in the research, but I think a lot more will be done because as a whole, we know that this is also the reason for the conference. There are so many interesting research and topics that require more investigation, like to collect more data to elaborate the decision tree model from more companies for more strategies as well, and forming more comprehensive bargaining power analysis. Here, our research is based on market share. But for example, in future, if we have more data, we can base on, for example, assets and liability of the companies as well in order to analyze the bargaining power. And computer program can be used to make systematic analysis as well. So this is all for my presentation. Thank you very much. And I would like to also thank the organizers for inviting me to give the talk. Thanks a lot.
Thank you, Prof. Lam, for the presentation. Does anyone have any questions for Prof. Lam? We can take one question. Okay, so due to time limitations, let's move on to the second speaker. However, if you have any questions along the way for Prof. Lam, please feel free to drop her a text via the chat window, and Prof. Lam, I suppose I'll be happy to answer those questions. So yeah, thank you so much, Prof. Lam, for for sharing with us on the thoughts which are indeed vital, especially for this all of these critical the transportation networks needed to for both the recovery as well as post disasters mitigation and reduction. Thank you so much, Prof.
Thank you.
Yeah. Thank you. Okay. Next, I would like to introduce to you Prof. Jesada Kanjana. He received his bachelor's degree in electronics engineering from King Mongkut Institute of Technology in 1999, master's in microelectronics from Asia Institute of Technology in Thailand, 2006, and PhD from the Japan Advanced Institute of Science and Technology in 2016, and a second PhD, I suppose, in engineering and technology from Sririthon International Institute of Technology, Thammasat University in Thailand in 2017. His research interests include data analysis and machine learning, reason with uncertainty, signal processing, and wireless sensor networks. He has worked at the National Electronics and Computer Technology Center in Thailand since 1999. So let us invite Prof. Jesada to deliver his keynote talk. Prof, please. The floor is yours.
Okay, thank you very much, Professor Dagan, for the nice introduction. I am going to share my screen. Please wait. Okay, can you see my screen?
Yes, I can see your screen.
Okay, thank you very much. Good evening, everyone. My name is Jesda Kanjana, a researcher of National Electronics and Computer Technology Center, or NECTEC, Thailand. It is my great pleasure, and I am honored to be a part of this amazing event, the virtual conference on disaster risk reduction under the theme of civil engineering for disaster resilient society. Thank you, Professor Siwasa, and also thank you, Professor Indrajit Pal, for giving me this great opportunity to say something about my current research activity. Okay, first thing first. Even though I am now leading some international collaborative research project relating to landslide, as the name, as the title of my talk might suggest, but I have to confess that I have no professional background in, say, civil engineering or geology or geotechnical engineering, like most of the audience here might have. I don't even know how to calculate the slope stability. So at the beginning, I did hesitate when the organizer asked me to give a talk, but when I thought that it might benefit someone and I might learn something new from the audience as well as the other speakers, I agree. The title of this talk is Real-Time Monitoring System Based on Wireless Sensor Network and Remote Sensing Techniques for Landslide Prone Area in the Northern region of Thailand. These projects, there are more than one project. These projects are supported by ASEAN Committee on Science, Technology, and Innovation, also partially supported by the ASEAN, the E-Asia Joint Research Program Funding Scheme. Okay. I will start with why the northern region of Thailand is of interest. This is the map of Thailand. Specifically, this is the landslide hazard map of Thailand, which is made available by one of our partners, DMR, Department of Mineral Resources. The topography of the northern part of Thailand is mountainous. Therefore, many regions are identified as a landslide prone area, as you see in the map, the green or the red area and the yellow area. Okay, I want to make it clear from the beginning that the aim of this project does not focus directly on policy or strategy or risk reduction or mitigation framework or something like that, or even the data interpretation. Those are in hand of experts in the field. Our main objective is to study how ICT technology can be used to get information from many sources, hopefully the useful information, under some practical conditions. For example, if we deploy a wireless sensor network to some prone area to collect data, the thing that we concern is how to make that network last longer, or how to minimize the power consumption, how to reduce the computational cost or computational complexity so that it can work in real time, or how to balance the energy usage among sensor nodes, something like that. We also investigate how to improve information quality. So this presentation will be divided in three parts. The first part, I will talk about landslide monitoring system based on wireless sensor network and visual IoT camera system. The visual IoT camera system, this part, has been developed by one of our partners in Japan, NICT, National Institute of Information and Communication Technology. The second part, I will talk about landslide detection based on multi-temporal satellite imagery analysis. And the last part, I will give some example relating to Rockfall detection from a LIDAR point cloud. In 2007, NECTEC, my organization, and one organization in Thailand we call DDPM, this yellow logo. DDPM stands for Department of Disaster Prevention and Mitigation. This department is under the Ministry of Interior. We developed the weather station network, and we use this weather station network as the early warning system for a landslide. We designed the weather station, so it equipped with many sensors, such as temperature sensor, humidity sensor, rain gauge, soil moisture sensor, light intensity sensor, and our weather station can operate by using solar energy with battery charger. Okay. And we install about 250 weather stations in the northern part in Chiang Mai province, Chiang Rai province, and Mae Hong Son province in the prone area. This is due to the fact that landslides that occur in Thailand, most of them are induced by heavy rainfall. So the strategy is straightforward. When the weather station detects the rain precipitation greater than some threshold value, that value is set by the expert in DMR or DDPM, then the system sends the signal, the message to authorized person or authorized staff who will handle the situation. This slide shows example of our weather station, one of 250, and this small panel shows the location that we installed in the northern area of Thailand. And this one shows an example of data that we can monitor via the internet. For some prone area, for some landslide prone area, we install a wireless sensor network to collect more data. And the wireless sensor network that installed in some area might be in the area that no 3G or 4G signal available. In that case, we develop an infrastructure that we call the relay station network. The only objective of relay station network is to forward data that collect from the wireless sensor network to one station that can access the internet, so that the analyst or researcher can analyze data further, something like that. And this slide shows an example of the structure of the wireless sensor network that we deploy in one experimental site. And for this work, we just want to compare two wireless protocol, wireless communication protocol. One is ZigBee, one is LoRa. We want to know that in actual environment, which one is more stable. So the objective of this study is to investigate the stability of two wireless communication protocol. And according to the data we collect from April last year to June last year, the y-axis shows the number of received package. We found that the ZigBee protocol has a package loss rate lower than that of the LoRa protocol, about 50%. And actually, we can compensate the loss of package by retransmit, but of course, we have to pay some price. In this case, we have it need more energy consumption. And at the landslide prone area, the one that I show in this figure, we install the camera system, the system that I said developed by NICT Japan. The motivation why we install the camera system from one report of DMR that say we can use the tree tilting to be the indicator of the cloud activity or slope movement, something like that. And one paper said that tree tilting can be used to indicate mechanism of slope movement. Therefore, if we have a series of images, then we can analyze the time series of image to identify such phenomena. So that is the reason why we install the camera system. This slide shows example. The small 6 images here show the image that we capture from our visual IoT system at different time of a day. So when we look at the images, we notice that the information contained in each image are different. For example, this image, which is captured around noon. So you can see that information at the middle is so clear, but we lost information in this area due to the shadow and in this area. But information in this area can be obtained by another image from the different time, maybe in the early morning, something like that. So if we have an expert to tell you, okay, we can use this image in our model, we cannot use this, we can use this, then fine. But if we don't have expert to select data for us, how can we solve this problem? So in this work, we propose a method that can fuse images in one day and generate a representative image of that day. If you are interested in this work, so you may check our paper, the image enhancement technique based on human visual perception and multi-exposure fusion for landslide prone area modeling system, which is published in one proceeding a few years ago, and another paper on this journal. If you are interested, you can email me. I can send you the manuscript. So that's it for the first part about the monitoring system and visual IoT camera system. For the second part, I will talk about landslide detection based on multi-temporal satellite imagery analysis. I will give you 2 examples. The first example, I will show you how can we detect the change in multi-temporal satellite image. This is the change detection in multi-temporal satellite images based on a technique that is called the structural patch decomposition and K-mean clustering. You may be familiar with this. And another example, I will show you how can we detect landslide area by using deep learning technique. In this work, we use very simple model, faster regional CNN model. Okay, for the first example, the input are to RGB satellite images, and the output is the change map. The map, this is a binary map that identify the change area in input images. Okay, and our method is based on two concepts. The first concept is K-mean clustering. If you're familiar with K-mean clustering, you know that we have to predefine the value of K. For example, we have this image. We want to cluster it into K groups, so we have to predefine the value of K. And to identify the suitable value of K, again, it is task of an expert. If we don't have expert, how can we do that? So we propose a technique that we call adaptive K-means. We don't need to predefine the value of K. The algorithm will try to find the suitable K for you. That is the first concept that we use in our work. Another concept, we use structural patch decomposition. Structural patch decomposition is famous for analyze the inconsistency in the structure of the sequence of images. So we can use this to detect the small change in images. So combine these two methods, we can get a very nice looking result compared to the conventional method. So for example, A and B figure, and A and B are the input images. E is our ground truth, the change in these two satellite images. D is the result we obtain from the proposed method. And C is the result obtained from the conventional one. So you can see there is no difference in this case. We test with many sets of data, but our algorithm is about 2 times faster. However, when the input image are noisy, for example, in case AD, we add some Gaussian noise to input image, or case of CD, we put add another kind of noise to the input image. You can see that the proposed method can still detect the change in the noisy satellite image, whereas the conventional PCA-based method cannot. You can see that. And another benefit of the proposed method, again, we have two input image here, A and B. E is our ground truth. The false positive of the proposed image is smaller than the false positive of the conventional PCA-based method. Okay, again, if you are interested in this work, you can check our paper, Unsupervised Change Detection in Multi-temporal Satellite Images based on Structural Patch Decomposition and K-mean clustering for Landslide Monitoring. Another example, this one is very straightforward. We train the faster CNN model by the satellite images, okay, to identify the landslide zone area. And by using this very straightforward strategy, the accuracy is about 70%. And then we have an idea. What if we train our model by another source? For example, we convert DEM, digital elevation model, to grayscale image, which will look like this, and then train our model by this DEM image. We get the accuracy about 65% lower than the RGB image. But if we combine these two models together by a very simple fusion model, like the session tree, very simple one, the accuracy improved considerably. So we are investigating this point at the moment. Okay, that is it for the second part. For the last part, I will show you example of our recent work on Rockfall detection from LIDAR point clouds. Again, I will give you two examples. One is cluster removal algorithm based on grid density, and another one non-parametric. We call it non-parametric density-based spatial clustering of application with noise, or this word density-based spatial clustering of application with noise. Sometimes we call it DBSCAN for short. Please pay attention to this part, the middle part. This is the general framework. If we have two 3D point cloud at different time of some surface, then we want to detect the displacement between those 2 point cloud. This is the general framework, the conventional framework. Okay. We have some pre-processing process such as image registration, subtraction, and then noise removal. The standard algorithm that we use to remove noise is NNCR. NNCR stands for nearest neighbor cluster removal. Okay, and after we remove some noise, then we can use the algorithm DBSCAN to identify the Rockfall area. For example, we have two 3D point cloud of the surface, one surface at different time, and after we input them to this process, we will get this cluster of Rockfall event. For example, in this figure, we have 1, 2, 3, 4, 5, 6 Rockfall events, something like this. When we investigate the standard framework, we notice that NNCR has one pain point. That is, the computational complexity of NNCR is quite large. That means when the input size increase, the computational time will increase a lot compared to the increase of input size. So we first try to replace the large computational time in noise removal process by our simple method that can use remove noise as well. We call it the cluster removal based on grid density. Okay, we test our work with database provided by this research group, Abelan. This is the surface of one cliff in Spain. Okay, you can notice the middle part of figure C and D. The results from the proposed method here use our cluster removal based on grid density and the standard method. Okay, actually we get the same result, but the difference is on this graph. The red graph is the plot of the data size, input data, the size of input data and the computational time of the NCR, the standard one. And the blue, again, plot the size of input data and the computational time. You can see that when the input size increase, the computational time of NCR increase almost exponentially, while our proposed method just about constant or just increase linearly with a small slope, like that. Again, if you're interested, you can check our paper here, Rockfall detection from terrestrial LIDAR point cloud by using DBSCAN with cluster removal based on grid density. The last one, as I mentioned in this framework, the important part to identify the Rockfall event is DBSCAN. And for the standard DBSCAN, we need to predefine parameters. And the performance of predefined parameters are very crucial. For example, you will get the result as shown in image E, figure E, if you use wrong parameters. And how can we identify those parameters? Again, we need the help from experts. If you have experts nearby, then fine. But what happens if you don't have the expert nearby? So we try to implement a new algorithm based on DBSCAN by that can perform the same task, but we don't need those two parameters. We call it non-parametric DBSCAN based on the divide and conquer approach. So, and when after we evaluate our proposed new version of DBSCAN by objective measure, and in this literature, the standard evaluation matrix is purity score. Our purity score is greater than the conventional one. And interestingly, in some case, for the standard DBSCAN, it cannot identify some event. For example, in this case, the standard DBSCAN identify that this is only one log4 event. But our proposed method, DBSCAN, we call it DBSCAN. DC stands for divide and conquer. We can identify 2 log4 events. So that's it. This is the conclusion. I show you some way that we can use ICT to get and to improve the quality of data. I gave you a few examples of our work. And of course, this is the quite big project that we have many collaborators, and this show the member organization who join in this project. Okay, thank you very much.
Thank you so much, Prof. Jasada, for the very informative and interesting, a wide range of the remote sensing techniques that you have actually shared, and the various case studies. So I guess that you'll be able to see that that there are several questions from the floor, and I think that okay, so I'll probably just ask probably 1 or 2 of these questions because of time. So first, would you please tell me with how do you distinguish the permutations due to noise, bad signal due to bad weathering, errors in filtering, randomly hacked software used with the genuine true measuring data? At least 3 measurements to check the fact, isn't it?
Sorry. You mean the question that that posted in the chat, right?
Yes, yes.
Oh,
yes.
okay. Wait.
Yeah.
How to distinguish perturbation due to noise, bad or that? Okay, hack software used with genuine true. Oh, this. Okay, very tough questions. Actually, all of the method that I propose, that I present today, we just simulate the data. We have genuine data, right? And then to evaluate the proposed scheme, we assume that we simulate a new data from the genuine one. So far we don't test with the data that we acquire from the actual environment. In the future, we will try to do that. So I cannot answer this question, a very tough one.
Okay. Yeah, because this was something that I was actually thinking about, because I think there was one example whereby you put some the Gaussian noise. Yeah, so the Gaussian noise, indeed that you will be able to see lots of scatter and patches. However, if there are some that probably just a small part of the image which might be affected, like say for example, due to cloud cover for certain the satellite image, then that could be issue. But certainly that we'll look forward to more papers from you, on this aspect, and to learn more from you.
I will put my email address in the chat, so if someone have questions, so you can email me, okay, and I will try to answer, and maybe we can try to find the answer together.
Okay, yeah, that would be nice. Okay, so probably just one last question. Another question is, can you tell me the threshold values considered during the stages of preparing the monitoring system, and the number of sensors generally that would suffice the study? I think this is also a very interesting and very pragmatic question.
Yes, as I mentioned at the beginning, we are not expert. Actually, NECTEC, we are not expert in geological or civil engineering, something like that. So we need an expert from Department of Mineral Resources who set the threshold value. So I don't know how to set it. So some experts just tell me what the threshold value you want, and I will set it for you, something like that.
I see. So you are looking more from the technological aspects.
Yes.
From the programming, the software aspects to try to. Okay. Yes. Right. Okay. Yeah. Thank you so much, Prof. Jasada, for the for presentations. Shall we move on to the next speaker? Next, we have Dr. Amaradan HD. He is an assistant professor in the Department of Civil and Environmental Engineering at IIT Patna. He has obtained his PhD from IISc at Bangalore in 2015. Previously, Dr. HD has held the short-term research position at the University of Milan in Italy, UPC Barcelona Technology in Spain, and NUS in Singapore, where I'm from right now. So before his PhD, he has also worked as a geotechnical engineer in Keller Ground Engineering India Private Limited in Mumbai for 2 years. He has published 2 books and more than 50 research papers in well-known journals and conferences. He's a life member of several professional organizations, including ASC, ISSMGE, IGS, ISCT, etc. He is a member of the Technical Committee on Reinforced Field TC218 of the ISSMGE, which is a very prestigious and a very well-known technical committee. He's also a technical committee on geosynthetics of Geo Institute of ASCE from the US. So let's welcome Prof. Heshda to deliver his keynote.
Yeah, thank you. Okay. Yes, good evening to one and all. Firstly, Dr. Shion, thank you very much for the very nice introduction. And I also would like to thank Dr. Shivalsa Kolatyar and entire his team for giving me this opportunity to be part of this nicely themed conference on disaster risk reduction with a special focus on civil engineering aspect. So it's my pleasure and privilege to be part of this wonderful virtual conference. So generally, whenever we hear about the term disaster, generally the natural disaster like earthquakes, landslides, or cyclones, these kind of disasters generally comes to our mind. So I'm going to talk a slightly different type of disaster, which is a man-made disaster. Okay, I'm going to talk about the disaster due to the vibrations. Okay, so vibrations are basically causes the failure of the buildings. It can lead to a cracking of the building, and also it can lead to a failure of the structures. So I'm going to talk about a novel technique which we are trying to develop here at IIT Patna for reducing the intensity of this kind of vibrations and also to protect the buildings and structures from the ground-borne vibrations. So what I do is that before moving to the technical aspect of my presentation, would like to convey best wishes from my institute, which is IIT Patna. And IIT Patna is basically located in the city of Patna, which is capital city of the state Bihar in India. And our campus is almost 500 acres in size, and we have a very beautiful campus. And our campus is very near to the holy river Ganga. And I take this opportunity to all of you from the different parts of the world, different parts of the India. Please do visit our campus if you are visiting this part of the country. So this is how I plan my presentation. Basically, what I do is that I'm going to talk about briefly about the different sources of vibration and how these vibrations will create failure or the disasters in the larger term, and how to isolate this kind of vibration, what are the existing strategies, and also would like to share the new methodology we're trying to develop, which is basically a cost-effective way of isolating these vibrations with the help of some field experiments and also 3D numerical studies. And finally, I'll try to summarize our research findings. Sorry. Okay. So vibrations are very common nowadays. It can be generated from the various construction activities. It can also generate from the movement of the vehicles or from the trains or the vehicles. It can also generate from the industrial structures, from the machine foundations. So from the vibration source, typically these vibrations will travel along the ground surface as a surface wave, specifically as a Rayleigh wave, and these waves can damage the nearby structures. As long as these vibrations are within certain permissible limits, buildings will be performing. Else, it will lead to a failure of the buildings, it will lead to a cracking, and in the larger term, it will cause some amount of disasters. So surface waves can be extremely dangerous, but some part of the vibration will also travel along the deeper stratum as a body waves, but these waves are not so harmful. But the Rayleigh waves or the surface waves will generally causes the failure due to this kind of vibrations. And these are some of the photographs which I have taken during one of my site visits nearby Patna. And this particular building is very near to the main railway track, Delhi-Kolkata railway track. And due to its frequent movement of the trains, we can see a lot of cracks in the building. So these all sort of cracks in the structure, in the floor, everywhere. And this kind of cracks can lead to a disaster. It can lead to a failure of these kind of buildings. So each countries basically have their own guidelines for these vibrations, and they have developed their own threshold values. And below this threshold value, if the vibration is there, then there is no harm to the building. But the instance the vibration exceeds a particular limit, then the buildings can be subjected to some amount of risk. So generally, these vibrations are measured by a unit called, or by a parameter called peak particle velocity, which is nothing but velocity of the particle due to the vibration. Okay, under the vibration, particles will vibrate. That velocity, if you measure in a 3 orthogonal direction, and if you take the average, it gives a peak particle velocity. And different countries or different standard codes have their own guideline, be it a AASHTO, British standard, or German standard, or Swiss standard. All these have their own guidelines for the threshold value of the vibration. Okay, so these vibrations are categorized into sensitive buildings, then domestic buildings, and the industrial structure. It also depends on the frequency of the incoming vibration. So frequency of the vibration again depends on the source of the vibration. If it's a railway vibration, the frequency will be somewhat different. If it is a machine foundation, the frequency will be different. But as long as these vibrations are within these permissible limits, then there is no problem as such to the buildings. Instance, it will exceed this particular threshold, then it can lead to the cracking in the building. So whenever it exceeds this kind of threshold limits, the isolation aspect comes into picture. So isolation in the sense, it is nothing but reducing the intensity of the vibration or protect the structure from the incoming vibrations. So if you look into the literature, there are various isolation methods are being followed all over the world. So most popular one is wave barriers, in which we create some sort of open and infill trenches for isolating the buildings from the vibrations. If it is a machine type of loading, then we can go for absorbing systems like springs or rubber coil systems. Else, we can also strengthen the ground using any one of this method for altering the incoming waves. So the most popular one is basically these wave barriers, open trenches or the infill trenches. So in this trench system, how it will operate is that, so this is basically a source of vibration, and we will basically create a shallow trenches near to this source of vibration. So since the vibration waves are basically surface waves, these shallow trenches will create some sort of obstruction for the coming waves. So hence it will reduce the intensity of the vibration. So these trenches can be open trenches, or it can also be infill trenches. We can fill some absorbing material here. So if the trenches are placed near to the source of vibration, we call it as active isolation system. If the trench is placed near to the structure to be protected, then we call it as passive isolation system. This particular system is relatively effective and good efficiency in isolating the vibrations. But only the concern is that the depth of these trenches. Generally, the depth of the trench varies from 3 to 4 meters. Okay, if you consider a scenario in an urban area or a soft soil where creating a trench of 3 to 4 meters deep is extremely challenging, because due to safety concerns or due to environmental issues or also due to stability aspect. So in those cases, we also feel sometimes with the infill soil, and this will slightly increase the stability, but the efficiency wise, it will not improve that much. So because of this, all these limitations, what we are trying to propose is that we're trying to develop some sort of a new sort of a isolation system, which can be placed just below the vibration source. I can say it as an active isolation system, because which is placed exactly below the vibration source, and which is made up of material called geosynthetics, which is a polymeric material. And we are proposing to use material like geocells or the biaxial geogrids to be part of this vibration isolation barrier, such that which can absorb some amount of vibration. These geosynthetics are popularly used for increasing the bearing capacity of the soil or reducing the settlement. If they can absorb some amount of vibration as well, it will be a manifold benefits, I can say, bearing capacity wise, settlement wise, and also isolation of the vibration. So we can place this kind of material below machine foundation, below railway tracks, below the pavement. All these are major sources of vibration. And the reason for which we have gone for this geosynthetic material, because these are economical, and main thing is economical. We wanted to develop some sort of a cost-effective isolation system, and it facilitates easy construction. These are extremely durable and resistant to extreme weather conditions, and no heavy machineries or specialized skill power or the labor force is required to construct these geosynthetic structures. So because of all these advantages, we thought of using this material for developing a isolation system which can absorb the vibration. So these are the two materials I'm going to talk about. One is a biaxial geogrid, which is a planar type of geosynthetic material, and the other one is a three-dimensional type of geosynthetic material. We call it as geocell. In case of geocell, we fill this geocell pocket with some sort of granular materials, geomaterial like soil or sand, okay, which will help us to basically this geocell will apply all-round confinement to the soil, and overall it will improve the performance. In case of the biaxial geogrid, it will basically also improve the lateral confinement on the soil by virtue of frictional and passive resistance. So whenever we use this kind of material, it will basically generate some friction between the soil and the geosynthetics. We call it as frictional resistance. Also, these ribs will try to confine the soil, the movement of the soil. So by virtue of that, both these materials are known for applying the lateral confinement to the soil, and by virtue of that, they improve the performance of the soil. So now I enter into our experimental investigation. I can say it's a field experiments, field vibration test we have conducted just to demonstrate that this geosynthetic based isolation system can absorb the vibration and able to increase the isolation efficiency of the foundation beds. So in this experimental setup, initially we construct a foundation bed made up of geosynthetics, and above that we place artificial source of vibration using this mechanical oscillator. This oscillator can vibrate in a different frequency ranging from 5 Hz to almost 50 Hz frequency, and which is connected to a DC motor which will help us to change the frequency. And under this particular vibration, what we have done is that we have recorded the vibration along this ground surface. Okay, exactly below this vibration source, we have a reinforced foundation bed to a depth of almost 1.2 meter. And using the accelerometers, geophones, and also vibration meters, we try to record various parameters like acceleration, displacement, and all those parameters on a real-time basis. Using this particular computer, we have captured all this data on a real-time basis under the source of this particular vibration. And this is how the setup looks like. It is a very tedious experiment, I can say. Initially, we have to create a trench and develop this trench using geosynthetic foundation bed. Then you have to use various sensors on a real-time basis to capture all these physical parameters. And in order to demonstrate this low-cost protection system or the isolation system, we have considered 4 cases, which I'm going to discuss only 4 cases. It's only a part of our research. And initially, we have taken a normal foundation bed. There is no geosynthetics in which. And in the second case, we have used a geogrid, which is a planar type of geosynthetics below the vibration source. And in the third case, we have used a secondary geogrid layer below the primary layer, just to see the effect of this secondary layer on the primary layer and the overall vibration isolation efficiency. And in the final case, we have considered a 3-dimensional geosynthetic product, which is geocell. And we have also tried to fill this geocell with different infill condition in the field. So I want to show some photos of how we created a test bed. Okay, initially this kind of trench, we have to dig it up in the soil. Then we have to place the geosynthetics in layer. If you're going for more than one layer, we have to properly compact it, maintain the uniform density and the moisture content throughout the bed in order to maintain that uniform density. This is for the geogrid reinforced case. This one is for geocell reinforced case. We can see we are filling with some sort of a local infill soil, as part of this geocell soil. Then I can say that I don't want to get too much details into the material properties, what we have used, but I can say that this geocell, we used neolloy-based geocell, which is nothing but a commercial name of the geocell, and a biaxial geogrid made up of polyester were used as part of the isolation system. So this is a type of vibration load which were applied on the reinforced foundation bed. So if you look into the load, this load was varied from the frequency 5 Hz to 45 Hz. And each frequency, basically what it indicates is that it basically simulates the dynamic force of different magnitude. So we can change the magnitude of the dynamic force by either changing the frequency, or there is something called eccentric setting, because we are applying some sort of a rotating type of force. And using this equation, we can calculate the amount of dynamic force we are applying on the reinforced foundation bed. And I want to show some interesting results. So here, when we change the frequency of the vibration, we also initially try to record the displacement of the concrete block, which was used to support this particular vibration source. And with the increase in the frequency, at a particular frequency, suddenly the displacement basically got increased. In all the cases, this increase in the displacement can be seen. This is for unreinforced, single layer geogrid, 2-layer geogrid, and geocell. So this particular condition, we call it as resonance. In the resonance, what happens is that the frequency of the vibration basically matches with the natural frequency of the soil foundation system. Okay, and under this thing, suddenly the displacement shoots up. If you consider 4 different cases here, so due to the provision of the geosynthetics, we can see there is a drastic reduction in the displacement during the resonance. Okay, when you place the geocell reinforcement, with the displacement even under the resonance was within the permissible limit provided by the Indian standard. So from here onward, whatever the parameter I compare, like peak particle velocity, all those things, all are compared corresponding to this resonance condition. because it makes sense to compare all these parameters or the different reinforced bed under the resonance condition, because at that instance, the displacement will be maximum. So we tried to measure the peak particle velocity again on the reinforced foundation bed on the surface. We could only measure up to 2.5 meters because it's a field experiment we have conducted. And here, peak particle velocity, again, I told that it's a unit, or it's used to measure the intensity of the vibration. So 4 different cases we have compared here. One is unreinforced case, single layer geogrid, 2-layer geogrid, and the geocell reinforced case. Here we can see, if you compare this first case and the last case, there is a drastic reduction in the intensity of vibration or in the peak particle velocity. So if you calculate percentage wise, it's almost 50% reduction in the peak particle velocity was noted in the presence of geocell reinforced condition. Even geogrid reinforced case do provided the reduction in the peak particle velocity. And this gives us a lot of glimpses that these materials can able to somehow absorb the vibration or reduce the intensity of the vibration just below the vibration source. Then we also calculated basically the displacement on the reinforced soil bed, and we have calculated in terms of percentage reduction in the displacement. We call this term as PRD, which is nothing but the difference between the displacement of the unreinforced bed to the reinforced bed. And if you take the ratio of the unreinforced bed, we get this particular ratio, which just gives us how much displacement of the reinforced bed reduces under this particular reinforced condition. So here also, if you compare different cases with the unreinforced case, obviously the geocell reinforced case yielded us the maximum reduction in the displacement of the reinforced foundation bed. Almost more than 50% reduction in the PRDA was observed in the presence of geocells. Next, what we did is that we calculated the isolation efficiency of different cases, different reinforced conditions. So this isolation efficiency is basically calculated using this particular simple equation, where ARF is nothing but it is a ratio of displacement of a reinforced foundation bed to the displacement of the unreinforced foundation bed at a particular frequency and particular eccentric setting. And here we have compared the isolation efficiency for different cases, again, which is plotted with the distance. So I want to take your attention to this particular line where it is for geocell reinforced case. Here the efficiency of almost 70% was noted. So 70% improvement in the isolation efficiency as compared to the unreinforced bed was observed in the presence of geocell reinforced case. So this is a very good sign, but experimental investigation could not give us the mechanism why this isolation happens by providing this kind of materials, which can only help us to quantify, okay, this much times the vibration efficiency can take place. If you want to develop some sort of a mechanism, then we have no option. We have to go for 3-dimensional numerical modeling, because first of all, these field tests were extremely tedious. And secondly, we cannot see the distribution of stresses and strain in case of experimental studies. So for that case, we have also developed 3-dimensional numerical models just to find out the mechanism why this kind of isolation happens. And for that, we have taken 4 different cases again, as I discussed in the experimental condition: unreinforced, single layer geogrid, 2-layer geogrid, and the geocell reinforced case. So if you look into these numerical models, we have considered the subsoil profile also. If you look into this chunk of the soil, which is 15 meter by 15 meter by 10 meter deep, whereas our foundation bed was only 3 meter deep, sorry, 1.2 meter deep. So that means we have even considered the subsoil profile in the numerical simulation to get the accurate result. So one of the challenge of this numerical model was for the geocell reinforced case, because it has a honeycomb shape, it's a 3D shape. Modeling that actual shape itself is a challenge. So with all the difficulty, we could able to develop this numerical model to get that mechanism of the vibration isolation. So whenever we go for the numerical modeling, various biggest challenge in this is that the determination of the input parameters. So depending on the constitutive model we select, these input parameters vary. In our case, Moore Coulomb was used for simulating the soil, and geosynthetics can be easily modeled using the linear elastic model. So for that, we have determined all the input parameters in the laboratory. Interface plays a very prominent role. For that, direct shear test, modified direct shear test was conducted on the soil geosynthetic interface. Then tensile test can be conducted for determining the modulus of the geosynthetic material. Similarly, this modulus of the soil can be determined using simple CU triaxial test. So this was the subsoil profile in that location where we have conducted the testing. So same subsoil profile was considered in the modeling, including all these parameters were taken from the soil report. And these are the material properties we have considered in the simulation. I don't want to get into the details of the material properties, but I want to show some of the results. The first step in the numerical simulation is always to validate with some of the existing literature from the experimental study. So in our case also, we have validated our numerical model with the experimental results. So here, basically, all the 4 cases we have compared the experimental results with the numerical results. And once the model is tuned to behave as a experimental results, then we have used that numerical model for further evaluation. So I want to show this interesting contours, which was developed from the modeling.
I hope that I can try to conclude.
Yes, I take just 2 minutes from here on. Yes. So if you look into these contours, like in the unreinforced case, we can see the vibration is spreading to a larger zone. Okay. And the last case I want to draw, it is for the geocell reinforced case. Here, the vibration was basically confined to a very narrow zone if you compare with the first figure. And this is the advantage, when you use the geocell, the vibrations will confine to a narrow zone. And in order to understand where this vibration is going, then if it is confined to narrow zone, if you take a section somewhere here, we can get this kind of image from the 3D numerical simulation. So this is for the unreinforced case, somewhere around frequency of 30 Hertz. And the other one is for the geocell reinforced case. So in case of geocell, I told it is confined to narrow zone. So if you take the section, we'll understand what happens is that under this vibration source, the geocell will act as a medium for diffraction. It will basically diffract the incoming vibration and it will allow it to pass it to a deeper soil stratum. So the vibrations are basically moving downward, not in the lateral direction. Okay, which is not moving in the lateral direction, we can basically protect the structure which is situated very near to the vibration source. So we could measure the strain in the soil because strains play an important role, which tells us whether the foundation bed is undergoing any failure. In case of the vibration, we could not see any failure. In case of geosynthetic reinforced case, I don't want to get too much into details here. And this is the last slide before I conclude. So here we have also noted down or measured the strain on the geocell, okay, or the geosynthetics. So because generally geosynthetics will fail when the strain level reaches around 2%. So if you develop an isolation system, but geosynthetics fail under the particular vibration, then that system has no use. But if you measure the strain in the geosynthetic, under the vibration of different frequency from 5 Hertz to almost 35 Hertz, the strain values are around 0.6% to 0.7%. So what it indicates that these materials will not undergo failure under this vibration. So this can absorb the vibration, but still will not undergo any sort of failure. So in a way, we got a concluding evidence that geosynthetics can be potentially used as a isolation material for absorbing the vibration. And what happens is that the lateral spreading of the vibration can be substantially reduced using this geosynthetics. So out of the tested geosynthetics, geocells found out to be the better option. And as I told before, this kind of system can be used for isolating the vibrations of machine foundations, railway, and pavement related vibrations. So with that, I conclude. Thank you very much. I apologize for the chair that I took a couple of extra minutes. Over to you. Thank you.
Thank you so much, Prof. Amana. Indeed, a very comprehensive, a very thorough study here. I think they shared quite a fair bit of details here, which I mean the extension of the time, I think it's more than worthwhile for all of us to be able to hear what that you have to share. Indeed, very refreshing to actually to see how those synthetics able to offer that absorption, that mitigation of of the seismic impact on foundation. So as you can see from the chat window, that you have tons of questions. I know that time is not on our side, so probably I'll just pick just a couple of questions. So the first one that I would like to convey is what is the range of vibrations this can extend? So, and also to what extent can this be used against seismic loadings on structures? And if this fails once on loading, how much residual vibration isolation can this provide? I think this is pertaining to the geosynthetic that you were sharing earlier on.
Yes. So as long as the intensity of the vibration is considered, this we have tested up to 50 hertz and peak particle velocity in the range of 17 to 18 mm per second. So under that vibration we have tested, because experimentally we cannot go beyond that, because there was nearby structures also. And by extent we go beyond 50 hertz, our own building starts giving the cracks. So for that purpose, we have limited our study to 50 hertz and peak particle velocity in the range of 20. And the second question may be an earthquake related thing. Maybe Dr. Xian is the better expert. In the morning, he spoke nicely about resonance due to earthquakes and all. So I may pardon from that particular question.
Well, feel free to answer. I mean, no harm. There's another question. Do you think the Joule cells distributed the vibration to a larger area due to which is the efficiency has increased with the cells? Yeah, this is something that I'm also quite interested to find out from your insight, your understanding that what is the Joule cell actually doing, to
Yes.
the vibrations. Yeah.
Yes. So what we found from our 3D modeling is that when we take the sections at a particular level, so whenever vibration hits the ground, geosynthetics or geocells are placed at a very shallow depth. They sort of they will diffract. It will diffract the incoming waves, and somehow it will divert it into a deeper direction, not allowing it to laterally spread. So by virtue of that, vibration transfer deeper into the soil, not in the lateral direction. I can say diffraction.
Okay.
Yeah.
Interesting. Yes. Okay. Yeah. So with that, due to time limitation, so thank you so much for your sharing of the experiments and your thoughts. So I hope that you can spend some time to answer the rest of the questions after your talk at your own time. While I will move on to the next presenter.
Yeah, sure. Thank you. I'll do that.
Thank you. Okay, our last keynote speaker for this evening is Piyush Samui. Prof. Piyush Samui is an associate professor in Civil Engineering Department at NIT Patna. He graduated in the year 2000 with a BTech in Civil Engineering from India Institute of Engineering, Science and Technology. He received his Masters of Science in Geotechnical Earthquake Engineering in IISc, Bangalore in India 2004. He holds a PhD from the same University. In 2008, he was a postdoctoral fellow at the University of Pittsburgh in the US and Templar University of Technology in Finland. Both of these universities are very well known. And in 2010, Dr. Piyush joined the Center for Disaster Mitigation and Management at VIT University as an associate professor for his integrated research on the design of railway embankment. He was awarded Shamsha Prakash Research Award. Again, this is a very prestigious award by IIT Roorkee for his innovative research on the application of artificial intelligence in designing civil engineering structure. He was selected as the recipient of IGS Sada Risham Singh Memorial Award 2013 for his innovative research on infrastructure project. He was elected Fellow of International Congress of Disaster Management in 2010. He served as a guest in Disaster Advanced Journal, as well as the editorial board member in several international journals. So let us welcome Prof. Piyush Samui to deliver his keynote. Prof, please.
Thank you, Dr. Darren Chen, for your kind words about me. And thank you to Dr. Srivastava also for giving me the opportunity. He has done a lot of hard works to organize this conference and is very efficient to organize this type of conference. Thank you, Srivastava.
Thank you.
So, in my presentation, I'll try to give a new things. Not new, it's new for the civil engineering field, but it is quite well known in computer science and mathematics. And they are used in the field of disaster mitigation and management. So it's quite new things for who are work on the civil engineering field. So that's why I think I will try to explain this topic, and so people can ask the questions and they can ask me the questions anytime during my presentation. So nowadays we have heard about a lot of things about artificial intelligence. So what does it mean actually? That means if you go for the definition, it's actually a technique to train a computer so that it will behave like a human. How it is just like for example, you are learning a child that this is a laptop, this is mobile phone, this is water bottle, this is book. Now, if you show same type of things to the child will tell this is also laptop, but he does not know why it is laptop and why it is book or why it is water bottle. That's why the terms artificial come into the picture. So in my presentation, I will talk about what is AI, artificial intelligence. Then I will give some application of the AI in the very well-known field in geotechnical earthquake engineering, that is called liquefaction. And this is another technique that is called suborbital machine, that is also an AI technique. Then I will talk about that application of AI in the failure of slope, to determine the failure of the slope. That is also in problem of disaster mitigation management. Then I will talk a very recent newly developed AI technique that is called minimax probability machine regression. And then I will try to give a brief introduction about the big data, because nowadays in this people are talking about also big data and how to use this big data in the field of civil engineering as well as disaster risk analysis and then some general conclusion will be drawn from this study. Now, what is the artificial intelligence? It explores and investigates various type of intelligent behavior by attempting to create in the artificial. So when it is developed for in computer science, it is used for the learning natural language, understanding, deduction, all this by using the computer. And according to Marvin Minsky, artificial intelligence science how to pursue a computer that to exhibit such a type of behavior that conventionally require human intelligence. That means it will model the human intelligence into by using mathematics and by using computer. So I think if you come back to this figure, then you can get an idea that how this model actually work. For example, if we take that any type of coffee order, and then what we are doing by taking our nose, then after analyzing by using our brain, then we can tell which type of coffee it is. That means what is happening if you come to the means rigorously into the problem, smell acquisitions, because we are taking by nose, then data processing to the brain, then we are doing analyzing by the brain, then which type of coffee we are telling here also. Same thing we can do by the AI also. But if you keep some sensor here and sensor can take the data, sense that coffee order, then after analyzing the data, then the model will tell which type of coffee it is. So the basic things of the AI model is true. We record the data set. Without data set, we cannot develop the AI model. That's the very basic thing. We record the data set. And quality and quantity of the data is very important. Quality is very important and quantity also is very important for the data set. So that is the basic thing. We record the data set for development of the AI model. Without data, we cannot develop the AI model. Now, this is very well-known phenomenon of the liquefaction. I am not going to the details. Everybody knows that due to the soil liquefaction, a lot of buildings collapse. So as a civil engineer, if you want to do anything, then you have to check whether the soil will be stable or it will be liquefied. So it's a binary type of problem. Problem is like that, whether soil will be liquefied, yes or no. If it is yes, then we can go for the construction. If it is no, then we can go for some ground improvement technique. Hegre will know about all these techniques, how to do the ground improvement. Now the problem is that to calculate the liquefaction possibility of a soil is very complex task, because the problem is there is two things. That the soil liquefaction depends on the two parameters. One is the soil parameter and the earthquake parameter. And both parameters, soil is a very crazy material and earthquake is also very uncertain. So AI can use, if you use AI, it's possibility that it will give the better result. So we'll see that how it is giving the result. But generally we go for the in-situ test to get to the soil properties, component test and CPT, standard penetration test and MSW. These all tests generally used to determine the soil properties. Now, first technique I have used the support butter machine here. So basically, what actually liquefaction problem? Liquefaction problem is that you have a two type of data. One data is soil liquefiable, another data is soil not liquefiable. That means yes or no. Then you have to classify these two data, and then you have to tell which soil or which soil will be liquefied or not liquefied. That means if you look at this figure, there are two type of data is there. Now, if you want to classify this data set, then you have to construct one straight line. This is two-dimensional problem. But if you go for the liquefaction, it's not a two-dimensional case. It depends on a lot of parameters, earthquake magnitude, soil properties. It depends on a huge parameter. So problem is complex. So that means if you want to classify these two data, that means one common sense is that if the distance between these two data is maximized, then your classification will be good. So what is the main aim of the SVM is that you have to maximize this margin between these two data sets, which is opposite, yes or no data. So this is the basic things of the SVM model, and which data is very close to this line, that is called a support vector. They only use for the final prediction. Other data has no meaning for the final prediction. That means if you use around 200 data set, that means how many data is used for the to to develop this equation, that is very important, and that is called support vector, and that will be used for the prediction of the soil, whether soil will liquefy or not liquefy. Now coming to the, if you want to combine this problem with the liquefaction problem, so liquefaction basically depends on the two parameters, soil parameter and earthquake parameter. Whitman 1971, he told that if you plot this thing, then we can make a boundary here, and then we can classify soil liquefaction, no liquefaction. Similarly, here also, if you look at the come to the SVM, you can consider a lot of planes. But the big question is that which one will use SVM to get a better prediction. Now, this thing I will discuss in the next slide. So, if you just now have told that if the data set distance between these two data will be maximized, then the data will, then that model will be good. Now coming to the model of the SVM model, so there will be two input parameter, soil parameter and earthquake parameter, and output will be liquefaction or no liquefaction. So earthquake parameter is cycle ratio that we know everybody, we know this thing that is being applicable as CSR approach by using seed and edges. And the another parameter is the cone prediction data set, QC value, cone CPT value. So this is the X and Y, this is the all data set. So X is the input, that is CSI cyclic stress ratio and the cone resistance, and the output is the +1 or -1. Now, if you consider our linear hyperplane, that WX plus B is equal to 0. So that things, because if you see that there is a two planes is equal, one is the plus plane and the minus plane. So we have considered another two equation. If you add these two terms, then it will come in this way, and then you have to add one slack variable also, because simulating data always requires some contains some noisy data set, some uncertainty is there. To tackle this uncertainty, we generally apply this slack variable, and it should be greater than or equal to 0. Now this is the cone resistance value. Generally QC value will get from the cone prediction test, that is well known for the geotechnical engineering point of view. Now already I have told the data set is required to develop the model. So I have taken the data set from Chichi earthquake. Around 134 data set has been collected. Data set I have information about the cone resistance, cyclic stress ratio, peak ground acceleration, and soil condition of the during earthquake, whether soil will be liquefied or not liquefied. And then after getting data set, then you have to divide the data set randomly. Randomly means you taken any of the data. There will be no biasness when you are collecting the data set. There is two type of data you have to divide. One is the training data set that is used to develop the model. So around 70% has been used, 94 data has been used to develop the model, and remaining 40 data has been used for the testing data set. This is required to verify the developed model. And radial basis function has been used to develop the equation of the SVM. So this is the overall how to develop the model for the SVM model. Now coming to the result of the SVM model, so there are two parameters is there. During the training, you have to determine by trial and error approach. This is called a capacity factor C value. You have to check that which one will give the better result. This is very tedious job, and that is the one of the biggest limitation of this AI model, that these two parameters you have to do by trial and error approach. So what you have to do, you have to give some value of the C, then sigma value, you have to check the performance, and then you see that what is performance giving. If it is not good, then again you check. This is very tedious job by using MATLAB or C. And here actually, if you look at this, very nice result is coming that both the cases performance is 100%. That means whatever the data we are giving for the prediction is correctly predicted. A number of support vector, in this case, it is only 3. That means only 3 data has been used for the final prediction. Now, if you look at this, although the model 1 is giving very good result, the problem of the model 1 is that it's required the CSR value to calculate to use the model 1. But CSR always determined by this equation, and sigma B is the total vertical stress. So if you want to calculate the total vertical stress, you look at the soil sample, because so total vertical stress is equal to gamma into Z, gamma is equal to unit of the soil. But CPT test does not give any soil sample. That's why you cannot use this model based on the CPT data. So you have to do again another test. You have to take the soil sample and then go into the laboratory. Then you do the calculate the unit weight of the soil. Now that's why I have developed a model, another model that is called model 2. So only input parameter has been changed. That is, I have used only peak ground acceleration and cone resistance value. And output is 1 or 0 here. And the same training data set, normalization technique has been used. Same thing that has been used. In this case also, if you see that the performance has been not changed, and but number of subgroup data has been increased. Last time it was 3, now it is 5. So that means the model 2 can be used also for the prediction of the liquefaction potential of the soil. So now actually this HVM has given very nice equation. If you look at this equation, S is equal to sine is a signum function. It gives +1 when this value is greater than 0, and it gives -1 when this value is 0 or negative. So how to use this equation? For example, in a particular place, you want to calculate whether the soil will liquefy or not liquefy. That you have to put into the X. That means in that place, what is the peak ground acceleration value and what is the cone resistance value you will use in the X. And X is the input of the training data set. That means for I is equal to 1, you have to take the number 1 unit training data set and corresponding alpha value you will get from this graph. And corresponding yi, what is the soil condition for that data set, whether soil is liquefy or not liquefy, that is -1 or +1 you have to put. Then by using this equation, you can easily calculate that whether the soil will liquefy or not liquefy. So now, after developing the model, I have used the data set by other earthquake also in the global. So this is one Japan earthquake. So around 109 that I have collected all over the world. And one interesting point is that out of 1099 data, 97 data has been correctly classified. That means the model is quite good and it can be used for the practical purpose. So this is one point. So this is the liquefaction I have done now. Now this is also one thing. After developing the model, I have tried to give some what is the range of the liquefiable soil by using these two parameters. One is the cone resistance and the peak ground acceleration, that is in Gal. So if you do this, if this zone, if the soil coming to this zone, then soil will be liquefied, and if this soil is this zone, this soil will be non-liquefied. So this chart can be used by the practitioner engineer to judge whether the soil will be liquefied or not liquefied. Now coming to my second presentation is that is the slope failure is very common in India as well as all over the world. I'm not going to the landslide because landslide, if you take, then it will take a lot of parameter, rainfall, all these things. I'm using very simple model, whether I will use this input slope angle, height of the slope, cohesion, unit of the soil, water pressure, and angle of internal friction. So this is the all input of the model, and output is whether here also binary output, slope will fail or it will be stable. So here, if you look at same thing here, I have used this is the all input and failed slope and stable slope. And here also, I have already told that the data set is required to develop the model. So around 32 data has been collected all over the world, and 23 has been used for the training data set, and remaining 9 data has been used for the testing data set. So after developing the model, here also it's given a very nice equation, and this is the kernel function. That is I have used the spline kernel. Same thing, just like liquefaction, also you can use this equation to determine the particular slope, whether it will fail or it will be stable. So this is also giving very good result when you are using some other data set. Out of 15 data set, only 1 data has been misclassified. Now, actually, if you see my title, it is disaster risk reduction. Now I'm going to the little bit about the reliability and uncertainty analysis, risk analysis. Now I will apply that, how to apply this AI model to determine the reliability or probability of failure of a soil for liquefaction. So for any engineering system, we know that these two things is very important. One is the load and another is the resistance. When load is more than resistance, then the failure occurs. That means what is the margin of safety? Margin of safety is the R minus Q, where R is the resistance and Q is the load. If it is 0, that means it's very critical condition. So for the structure should be stable, this M should be always greater than 0. That means probability of M greater than 0, that is called the reliability. Now I have used first order second amendment method to determine the reliability index, that is mean of the factor of safety minus 1 divided by the standard deviation of the factor of safety. And probability of failure has been calculated by using phi of minus beta. Phi is the standard normal cumulative distribution function. So what is the drawbacks of this model is that it's sometimes a very time consuming method when there is an implicit performance function is there. And if you look at the CSR and CRR calculation, there's a lot of lengthy procedures there, so it will take more time. So that's why I've applied minimax probability machine regression. That is also one AI technique. So what is the difference between this AI, this minimax probability machine regression is that it can control the future prediction also. For example, when you develop a model, and then when you want to use the model in practical sense, then you have no control over the future. It can give any value. But in a minimax probability machine regression, what they're doing, they want to keep some bound plus minus epsilon. Within this, they want to predict, and that they are doing maximizing probability. This is the very latest development in 2002. That has been used to determine the reliability index of the soil liquefaction. So I have collected the different data set around all over the Bihar, and here also around 235 data set has been collected. So training data set and testing data set divided to divide. So 169 has been used as a training data set, and remaining data has been used as a testing data set. And here also, if you look at this, I plotted actual factor trajectory in the x-axis and predicted normalized factor safety in the y-axis. So if you look at that, R value is coming 0.85 for the testing and training 0.987. That means if the R value means coefficient of correlation, if the coefficient of correlation value is more than, is close to 1, then your model is good. If it is more than 0.8 in simulating problem, that model can be acceptable. So here also you can see that this model can be acceptable and it can be used for the practical purpose also. Now this is the reliability index has been calculated. This is the depth, how the depth on the depth it is varying, and this is one according to the depth in 1 dimension. So there is a, you can see that if the reliability index is minus, means the soil will be liquefied, because that if you see this equation, then the factor should be less than 1, and this is actually in 1.5 meter depth how reliability index varies into the Bihar, and this is 3 meter depth how its reliability index vary. So this you can get an idea about if you use the reliability index, then you can, then from that you can get the probability of failure, and then you can calculate the risks also. So this is the one of the approach how to calculate the reliability index of soil for the liquefaction. Now coming to the big data. Big data means huge amount of the data. There's a difference between the natural data and a big data. Big data is considered 4V. That is high volume of the data, and the frequency of the data is very high. Also velocity, variety of the data is very high, and veracity, the quality of the data. This 4V generally give the concept about the big data. What is SPT actually? So nowadays also, if you look at it today, also there is some point in all over the world, some SPT test has been done. So that's why this data is quite continuous. That means the frequency of the data is very high. Every day it's updating. And variety means all over the world will calculate the SPT data. So what they are doing actually, for example, if you can calculate the all over world data still today, SPT data, that require very huge storage space. And how to handle the data, that is the concept of the big data. Recently, one paper published into they have calculated that to predict the magnitude of the earthquake in computer geoscience. This paper give an idea how to use the big data in civil engineering problems, and we have a huge data amount. If you can collect the huge amount of the data set, then we can give a better solution to some existing problem. For example, I am telling about the liquefaction. If you can collect all over the world, whatever SP data we have, then if we develop the model, that will give always better result, because in AI model, always quality and quantity of the data is very important. I will finish within 2 minutes.
Okay.
So what is the conclusion? What you can take in the home? The past call conclusion is that performance AI is very database specific. Database specific means you cannot tell this model is the best you use for the all problem, bearing capacity, settlement of the settlement, pile foundation, slope stability, geocentric returning wall. No. You have to check every model for every problem, and you have to decide, you have to see that which model is the better. Second is the result. This is very important conclusion. The result of AI should be analyzed thoroughly, and decision should be taken based on the practical experience. That means you cannot use this AI result blindly. For example, AI is giving soil is liquefiable, and you blindly believe that soil is liquefiable. That means you cannot consider. You have to check. You have to visit the site, and you have to see the local profile there also. You have to take the judgment. You cannot use the AI result blindly. Last conclusion is that AI model can reduce the cost of the project by reducing the number of experiments. Because if we get the data set, then we can use this model for the getting the output. So we have to not perform again the test. So we can reduce the cost of the project. There are some of the books you can refer for this to understand this new concept of this and how to use this thing in civil engineering as all over. Thank you. Questions are welcome.
Thank you, Prof. Pudrash, for the very comprehensive and very enlightening talk, especially bringing in AI into civil engineering. The floor is open for questions. So if you have any questions, feel free to drop your questions in the chat window. Okay, so there's one question. The question is, AI models follow a hyperplane for classification. How much it suits the real problem?
Can you repeat the question? How much?
AI models follow a hyperplane for classification. How much would this suit the real problem in the field?
Yeah, that's a very good question actually. That when you're using that model, you have to be very cautious. See what is happening actually. One thing you can do nowadays, what they're doing, they are using 3-4 models. Then they are predicting that whether soil will liquefy or not. Then they're doing, they are saying that if every model is predicting soil liquefiable, if it is not, then you check which is giving the maximum. So if some, for example, you are using 5 model, then 3 model is giving soil liquefiable, and 2 is not giving. 2 is giving soil is not liquefiable. Then you go for the 3 model result. That is called the boosting trees or ensemble method. So you cannot judge based on the one model that soil will be liquefied or not liquefied. You have to use many model, and you have to take in the whole data set. That's why that big data concept is coming, because if you use whole data set all over the world, then you develop the model that will be more rigorous and more generalization capability that you can use for the practical purpose.
Thank you, Prof. The second question is, how did you fix the number of support vectors? What are the criteria for choosing the support vectors in SVM, which is the support vector machine?
Yeah, see, there is no criteria as such. See, it's automatically after when you are there is a two parameter is there in SBM. One is the capacity factor, another is the kernel parameter. These two parameters you have to give initially. So when you give this parameter initially, the model automatically after doing the optimization, the model automatically give you the number of support vector. But one thing is that if you want to make the model is good, then your support vector should be less. Then what will happen? The support vector is less. That means you are not depending very huge data set. So if you depends very huge data set, that means your data has a lot of noisy data is there. If you use the less data set, then you that is good actually for practical purpose. So it will be that number of support will be decided based on the optimization during the optimization of the problem.
Thank you so much for the sharing. Due to time, it's already 10:36. So I'd like to thank the four speakers for their generosity in sharing their thoughts, their expertise in their areas, and also thank you so much for the participants. We still have 245 of you around. So wow, this is really this really demonstrates that how the support for this conference as well as for the speakers. So on behalf of the organizing committee, thank you so much for the support. Please continue to support us for the rest of our sessions in the next few days. With that, I'll hand over to Dr. Srivastava to wrap up for the day.
Thank you, Dr. Darren, for the excellent and efficient moderation and for chairing the session. Thank you very much. Thanks to all speakers, Professor Jasmine, Dr. Jasada, Dr. Amarnath, and Professor Piju Swami for the excellent presentations. As you rightly said, still we have around 250 participants around. So the response and with the enthusiastic participation from the delegates is very, very exciting, and we are very happy with that. So we convey our special gratitude to all the participants who are making this conference a great success with your excellent participation. So tomorrow we have keynote session 7, which will be chaired by Dr. Indrajit Pal. And we have 4 speakers: Dr. David Bristow from University of Victoria, and Dr. Isabella from University of Salamanca, Spain, and Dr. Pablo from University of Auckland, New Zealand, and Professor Tahmid Husaini from Bangladesh University of Engineering and Technology. So we will be starting sharp 9:30 AM Indian time. So we request all the participants to kindly join 10 minutes, at least 10 minutes before the session. Chandan sir, Dr. Basanta, Dr. Darren, can we close the session formally?
Yes, yes, successful. Huh?
Yeah, please go ahead. It's a great program today.
Thank you.
Thank you all. So we formally end the session here.
Yeah.
Thank you. Good.
Bye-bye. Good night.
Bye.
Okay, good night.